This is Miss Plant's video in which I'm going to try and explain forces and their interactions for AQA Combined Science and GCSE Physics in 5 minutes. So first thing you need to understand is the difference between a scalar and a vector. A scalar just has magnitude. So for example, speed is a scalar, 30 meters per second is the value. Distance is a scalar, could be 10 meters. A vector is something that has magnitude and direction. So velocity is a vector, as in you would say, have to say 30 meters per second west. Displacement is a vector, 10 meters east. Sometimes you quote them like this. You could, if you're dealing with just two directions, you could just say minus or plus to refer to left and right for the vectors. Vectors are represented with arrows, which are drawn to scale. So the length of the arrow represents the value, the magnitude. So in this case, it's 3 newtons, and the direction just points in the direction. So in this case, I'd say that's 40 degrees to the vertical. And I've used the scale 1 centimeter as 1 newton. So that line's 3 centimeters long. So you know it's a 3 newton force. Now, you need to understand the difference between different types of forces. The two forces are separated into 2 categories, contact and non-contact. Contact forces are touching each other. They have to touch for the force to act. Non-contact are separate. They do not have to touch for the force to act. Contact forces include tension, so that's the force in a rope holding something up. Friction, when 2 surfaces rub together. Air resistance, when you move through air. And the normal contact force. The normal contact force is the force you get that keeps you up. So if you're sat on a chair right now, gravity is pulling you down. The chair is providing a normal contact force. It's like a sportive force when you put something on a surface. Non-contact forces include magnetic forces, so north poles, south poles. Electrostatic, that's positive, negative charges. They don't need to touch. And the gravitational force, which acts between any object with mass. Weight. Do a little bit more on weight, talking about the gravitational force. Weight is the force acting due to gravity. There are 3 things you need to know about weight. First of all, that weight depends on the gravitational field strength. And the gravitational field strength depends on what planet you're on, really, or if you're in outer space. So the moon has a lower gravitational field strength, so you weigh less on the moon. Weight is measured using a Newton meter, or more sometimes called a calibrated spring balance, if you write AQA specifications. This is what a Newton meter looks like-ish. You've got a hook, there's a spring in there, you hang something down and the spring will extend with related to the weight of the object. Weight acts from the center of mass of an object. If it's a uniform object like a square and uniformly filled, the center of mass is just in the middle, and the center of mass is the point at which the mass is concentrated or the weight appears to be act. So the weight does generally act like a force arrow. That's why you can have some of these like fancy balance toys where you put your finger on them and they'll balance. That's because your finger is directly below the center of mass. Right, you need to know how to calculate weight. Weight is mass times gravitational field strength. You need to memorize that equation. You are not given it. Weight is the symbol W, mass is M, gravitational field strength is G. Weight is measured in newtons, mass is measured in kilograms, and G is measured in newtons per kilogram. And you need to know that on Earth, gravitational field strength is 9.8 newtons per kilogram. Right. Resultant forces. So if you've got more than one force acting on an object, you can calculate the resultant force acting on it. And the resultant force is the overall force acting on an object, or the single force that could replace all the forces acting on it. So, if you had 10 newtons to the left, 5 newtons to the right, the resultant force would be 5 newtons to the left. Now, we can draw free body force diagrams to find the resultant force. So we've got a situation here where we've got a box and another box suspended. I'm going to draw a free body force diagram for the box here so I can work out the forces. Now, 20 newtons of the box's weight, because I've decided the box is 2 kilograms. That means there is a 20 newton normal contact force. So the force that keeps the box, prevents the box from falling toward the table, is called the normal contact force. And there is obviously tension in this string, pulling down, 30 newtons tension. So this is right before this box is going to move. Right before this box moves, this is the situation, meaning the resultant force is 30 newtons to the right. We could do B, but anyway. Obviously, as soon as the box starts to move, there'll be frictional forces acting. So this is an unbalanced force acting on it, and this is the free body force diagram for that box. Just clearer, we only do the forces that act on the body. Now, the next bit of this section is going to be in a different video. Vector diagrams. Vector diagrams are hard. It's higher tier only. And when I say higher tier only, it's the top end of the higher tier. So these vector diagrams on this next video are hard. So if you're not necessarily aiming for a 7 or an 8 or a 9, don't panic about them. Do your best because it's worth trying to grab a few marks. But if you're not aiming for that high level, you don't necessarily need to panic.